So since the 10th board exams are coming up, in this video we are going to revise the similarity chapter from Maths 2. So we are going to go slowly and take a look at all the main concepts in this chapter so that you can just look at this video and be prepared to solve any question that comes from this chapter. Without any further ado, let's get started. So first of all, we just have a simple note saying that if there are two numbers n and m which we divide, so we can say that they are in the ratio m is to n. This is just another notation to write these type of numbers. And the area of a triangle is half into base into height. So this is very important since this whole chapter is about triangles. So now this is one thing that you should keep in mind, and this will be used throughout this chapter, that since we know that the area of two triangles is just half into base into height, and let's say there is another triangle with its area half into small v into small h, half into base into height. Since we are dividing this, we can just cut this half, which is done over here, and we can see that from the example of these two triangles, if there are two triangles, we can say that the ratio of their areas, since we are dividing, we can just cut the half, is always just the ratio of the base into height into the base into height. So this isn't much of a derivation, it's just a simple thing that the halves gets cancelled because it's both in the numerator and in the denominator. But since we use this thing directly in a lot of proofs, you just have to keep this in mind. Going ahead, this again is just a simple condition saying this is just a variation of this formula saying that let's say if the heights of both the triangles are equal, so this will both become h. So since then we can just cut this from the numerator and the denominator, and the ratio will only become the ratio of the bases. And again, the next thing is just similarly, let's say the bases of both the triangles are same. So then this B1 can get cut and cancel out, and we can just say that the ratio of their areas is only the ratio of their heights. It is just simple algebra. So we'll not spend too much time over here because you have already seen these concepts, and it's better to spend your time practicing right now instead of trying to memorize this. So again, this is just fill in the blanks. So we are given two triangles, that is A, B, C. So the full outer bigger triangle, this one. So this, and the triangle APQ. So let's take a different color. So A, P, and Q, which is the inner triangle over here. And we have to write what is the ratio of their area. So first of all, it is just the base into height upon base into height. So the B, it will be BC into the height is for both the triangles AR, and the over here it's PQ into AR. And since both the AR is at both the places, and since in these triangles you can also visually see that both of them have the same height, we can just cut this AR and we can cancel this AR, and we can write BC upon PQ. So other questions are also very similar. So let's not solve all of them and move ahead. After this, we will come to our first theorem. So this is the first theorem for this chapter, which says that let's say we have a triangle. So if we draw a line which is parallel to the base of the triangle, then the ratio that we divide the sides into, that is the ratio AP upon PB. So this upon this will always be equal to the ratio on the other side. So let's say this AQ upon QC. So that is AQ upon QC. So now how do you prove this? So first of all, you always draw this diagram. So let's say we have to prove this theorem in the exam. So what we'll do, first of all, we'll draw a triangle. After you draw a triangle, just name all the sides. So we have A, B, and C. Then we draw a line. So this is a line, remember that. So it extends in both the directions infinitely. Let's call this L. And we just say that L is parallel to BC. So we are drawing this line L such that it is parallel to BC. So we already have this given. And then we just extend this. So let's also name these points where the line intersects the sides P and Q. And then we extend this using dotted line from Q to B and from P to C. So now we have this triangle over here ready. And in this, the main concept that we are using to prove that this upon this is equal to this upon this is just the same logic of the ratio of the areas that we saw in just a little bit earlier. So what we do is, first of all, we have to take the area of two triangles, which is this upper triangle and this triangle. So we can say that the area of this triangle upon this triangle, and since these both triangles have the same height, PQ is the height over here, right? You can see that PQ over here is the same height for both of these triangles. The ratio is just going to be the base. So the base for the upper triangle is AP upon PB. So this is the ratio for the area of this triangle and the area of this other triangle. Now we again take this triangle the same. So the ratio is AQ upon, since over here, let's say, and this triangle. So again, PQ is the same height over here. And so we say that the area of this triangle upon the area of this triangle is just the base ratio of the bases. So AQ upon QC. So just for a recap, for a quick recap again, what we did was nothing very complex. We just draw a simple triangle. We draw a perpendicular line. We extend this over here. We extend this over here. And then we consider the triangle, the upper small triangle that is formed over here. So if this is a triangle, there is a triangle that is being formed over here when we draw a line like this, right? So we take the area of this triangle and then we compare that, or we take the ratio of that with the two dot simple triangles that are formed inside that we draw using the dotted lines when we connect the points made by the crossing line and the opposite point on the base. So we join them in a crisscross manner. So now we have these two ratios. Now what we do is we consider these two triangles, and since these two triangles have a common base, so that is PQ, and they also have equal height. Why? Because L is parallel to BC that we already have given. So that means that the distance from this point to this point, any point on this line, and if the shortest distance from any point in this line to the any point in this line will be the same, right? So that is in a sense saying that the height of this triangle is the same as the height of this other triangle. So the height of triangle PQB, so triangle PQB, the height of this is the same as the height of PQC, because this length over here is the height for both the triangles. So because of that, we can say that since the height is also same and since the base is also same, the area of both these triangles are the same. Why? Because the area is nothing but just the base into height, half into base into height. And since if the base and the height both are the same, the area of both the triangles will be the same. So using that concept, you can say now we can come to the fact that AP upon PB, which was the ratio of the areas of this triangle and this triangle, is equal to the ratio of AQ upon QC. So I'll draw nicely on this. So again, let's take it slowly. So first of all, we found out that the ratio of the areas of this triangle and this triangle over here is nothing but AP upon PB. Why? Because the height of both the triangles is the same. So the ratio of the areas is just the ratio of the bases. Then we took the ratio of areas for these two triangles. So which is just AQ upon QC with the same logic. And now we can say that these both things are equal because we proved that this triangle over here, let me shade it in yellow, has exactly the same area as this triangle over here. And why is that? Because they both share the same base and the same height. So now we can say that this triangle, the upper triangle, the ratio of the area of this triangle upon this lower triangle will be equal to the ratio of this upper triangle upon this other lower triangle, because both the ratios just have the area of the upper triangle, and below we have the area of this other triangle in one ratio and this one triangle in the other ratio, but both of the areas are equal. So that is why we can just say that AP upon PB equals to AQ upon QC. So this was a very intuitive walkthrough of what this theorem is and how do you prove this in exam. But obviously you have to practice this once or twice, because in exam you have to write the correct notation. So you can't just say that, okay, this and this are equal. You have to first say that we are considering the areas of these two triangle and we get AP upon PB, which we just got over here. So we are doing the same thing again. So then we consider the other areas. So proportionate to bases, which we just saw. And then again over here, we say that since these two triangles, so these two triangles, the PQB and PQC, they are nothing but these triangles over here, the inner triangles over here. And we say that they both have the common area because they both have equal heights and they have same base. So we say that the area of both of them is equal. And because the area is equal, this equation over here will be true, right? Because the numerator is same in both the equations. We are just taking the area of this upper triangle over here, divided by once we took this area and once we took this area. But because both of these areas are same, which we just proved over here, we can say that this full equation is true. And because of that, we just equate these to each other. So it might seem like a lot of stuff going on, but if you practice this once or twice, you can see that this is a very short proof and you can easily remember this in the exam. I'm repeating it again and again just so that it fits into your brain and you don't have to think about this a lot, and you can easily recall it in the exam time as well. What you do is you just draw a triangle, draw a line parallel to the base, always give names to all these points and all the lines. That is just common in any proof that you make, and then you have to just connect these points in a crisscross manner, and then you just take the areas of this triangle with this triangle and again this triangle with this triangle. Then you prove that both of these triangles have the same area, and therefore you can say that this upon this is equal to this upon this. Now the next thing is just the converse of this theorem, which says that if AP upon PB is equal to AQ upon QC, then this line is parallel. So these type of theorems always have a converse theorem as well, so you can just keep that in your mind. So this is just a activity which you can perform, and this is just to show that when there is a angle bisector, you have the ratio of this and this. So AB upon BC will be the same as AD, which is this and this DC. So the proof of this thing is shown next. And now we come to the second proof of this chapter. Again, this proof is also very intuitive and very, very easy if you follow along. It just looks very big because you have to write everything explicitly when you're proving a theorem. But otherwise, if you see, it is very easy to prove. You just have to draw a simple triangle. Then what you do is you have an angle bisector over here. So let's say this is C, this is A, and this is B, and let's call this point E. Now we know that this angle and this angle over here are equal because this is angle bisector, right? It is given that CE is angle bisector, so that's why the angle ACE and ECB have to be the same. So now what we do is we just make a line that is parallel to CE. So a line parallel to CE would look something like this for this triangle. And then we extend this AC so that it meets at point D. And now what we do is we just have to prove that this angle over here and this angle over here is also equal to this angle and this angle over here. And after we say that all these four angles are equal, we can say that this CD over here, this line segment over here, is equal to this line segment over here. Why? Because there is a theorem that says in a triangle, if there are two congruent angles, the sides opposite to them are also equal. So how do you do that? That is the main part. So let's go ahead and see that. So first of all, the we say that angle ACE is equal to angle CDB. So this angle over here, ACE, is equal to this angle over here. And why is that? Because we have two parallel lines and a transversal. So to understand that concept better, let's say there are two parallel lines and imagine this being a transversal. So in a transversal, you have two angles over here. So this, and these are called corresponding angles, and these angles are always equal. So if you look at this diagram and if you imagine these two lines to be the parallel lines and this AD to be the transversal, this and this angle are the corresponding angle. It is very similar to this diagram. It is just tilted 90 degrees that way. And then the next part we say is that this angle over here is equal to this angle over here. And why is that so? Because again, when there are two parallel lines and there is a transversal, the angle over here and the angle over here are equal and they are called alternate angles. So there are proofs for that as well, but we are not going to dive deep into that. You just have to remember that these are equal. So because these are equal, now we have proved that this is equal to this over here and this angle other one is equal to this. And because we already know that this angle over here, ACE, the angle ACE is equal to angle ECB because these angles are made by an angle bisector, and by definition angle bisector is a line that divides the angles into two equal parts. That means these two angles are equal, and since this angle is equal to this angle and this angle is equal to this angle and these two angles are both are equal to each other, this angle is also equal to this angle. And that is what we actually wanted to prove. Because when we prove that this angle is equal to this angle, we can say now that this line over here, this line segment CD, is equal to this other line segment over here, CB. Why? Because of this theorem, the sides opposite to the congruent angles. So if you see till this part, almost you can say that this is around 90% of all the proof. We are just doing that. 90% of proof is just trying to prove that in this setup over here, let me draw that again. In this setup over here, so this setup over here, let me actually just show it in the actual diagram itself. So in this setup over here, we are just proving that CD, this line segment, is equal to this line segment. And why is that? Because once you prove that, you just can use the theorem that we just saw earlier, this theorem over here, that if there is an angle bisector, then this ratio AP upon PB will be equal to this ratio AQ upon QC. So if you apply this same theorem to this triangle over here, and let's say that CD is parallel to DC. And why? Because we drew it that way, right? We chose to draw DC, DB. I mean, we chose to draw DB parallel to CE. So that's why now in this triangle, if you see, we can have the ratio AC, which is this, upon CD equal to, so I'll take a different color, AE upon EB. So now we almost have the result that we want, but we have a CD instead of a CB. But since we already proved that CBE and CD are same, we can just write a CB instead of a CD. And this is the result that we were trying to prove, that in this triangle over here, the ratio AC and CB is equal to AE and B. EB, AE and EB. So this is the proof over here. So again, a very easy proof if you remember the intuition. And how do you prove it? Again, just you have to remember this construction of what we are doing. And then you just have to remember that we have to prove that all these four angles are equal. And when you prove that, you are able to prove that these two lines are equal. And when you prove that these two lines are equal, you just use the theorem that we learned earlier and then substitute the line over here, and then you get the result that you want. And once again, you have to practice this. There is no other option because you have to learn the notations as well. But if you learn this intuition, you will never forget how the theorem was actually proved. So let's move ahead. Now again, one more property of parallel lines. So it says that there are three parallel lines and there are two transversals of those parallel lines. So these are the three parallel lines and there is this transversal T1 and transversal T2. And the theorem just says that these ratio over here, AB upon BC. So AB upon BC will be equal to the ratio found by the other transversal as well. So that will be PQ upon QR. And this is also again very, very easy to prove. This is just a three-line proof actually. So I'm not even going to go through the proof over here, but I'll again give you the intuition. You can just cross connect these two dots, the dot P and the dot C, and this gives you two sets of triangles. So one set is this triangle over here and this triangle over here. So this gives you these two triangles, and in these two triangles, you can consider this as the base, and you can consider this as the parallel line that is passing through the other sides. And again, we use the theorem that we learned earlier. This theorem over here that we learned earlier, the first theorem that we learned in this chapter, we use it again in this proof over here. And what we do is we find that the ratio this upon this, so that is just AB upon BC, will be equal to CD upon DP, right? CD upon DP. And this ratio over here, PQ upon QR, will be equal to the ratio again over here, CD upon DP. Why? Because this is just this triangle. You can consider this triangle, and if you consider this other triangle, then this is the base and this is again the line that is parallel to the base, and you use this theorem again, the first theorem that we learned. And now as you can see, this part and this part both are equal to the same thing, so that means we can just equate both of these together, and that gives us AB upon BC equal to PQ upon QR. And this is just the result that we were trying to prove. So we are just writing this in proper notation in the proof, and the proof is fairly small. So I'm not going to go through the proof again. So let's move ahead. So again, this is just all the things repeated. So this is the proportionality theorem. So these ratios over here, then the angle bisector thing, and then this three parallel line thing that we just learned. So we have some questions on this, like you might be given the length of this line, and this line, and maybe asked to find the length of this line, AE, and you can find it easily because you know that the ratio is the same and that you just have to substitute the values. So there are a lot of practice questions. Obviously, solve them if you want to actually be very familiar with these concepts. But since this is a quick revision video before your actual examinations, we are not going to go through everything in this. We are just going to go through all the syllabus so that during the exam, you can apply logic for questions like this, but you do not forget the proofs and the formulas. So now let's come to the last part of this chapter, and that is about similarity. So first of all, it is just giving us a little bit of a recap saying that if there are two triangles and they are similar. So if these triangle and this triangle, they both are similar, that means that their corresponding angles are the same. So this triangle and this angle is equal to this angle equal to this angle, and this angle equals to this angle, and their sides are in the same ratio. So this ratio over here, AB upon DC, so AB upon DC will be equal to the ratio of any other side. So let's say BC and EF. So BC upon EF. So that is just to say that all the sides are growing in the same ratio. So that is by definition what similar triangles are. So now in this chapter specifically, we are going to learn three tests that we can use to find out if two triangles are similar. So the first test is if all the three angles of both the triangles are equal. So if we have two triangles and A equals P, B equals Q, and C equals R, that means both of these triangles are similar. And you can also just call this AAA test, that is the angle test, because we are checking all the three angles. That is why it is called the angle test. You can also call this test only AA test, that is the angle test. Why? Because all the three angles of any triangle must sum up to 180 degrees. So if you have uh, angle A plus B plus C, if these are the internal angles of a triangle, so like A, B, and C, they all must add up to 180 degrees. And since they all have to add up to 180 degrees, if for any two triangles, let us say there is an angle P plus Q plus R, this is for another triangle, and we know that A is equal to P and B is equal to Q. So now we know that this is equal to this and this is equal to this. We don't have to check C because now that we know that since these two are equal, since these two over here are equal, C is just going to be 180 minus A plus B, right? Minus A plus B. So this is what C is going to be. And even R is also going to be 180 minus P plus Q. But we then, since we know that P is equal to A and B is equal to Q, we can also write this also as A plus B. So as you can see, if two of the angles are the same, third angle of a triangle has to be the same. So you can just say that if two angles are same, then also the triangles are similar. The next test is the SAS test. So that is the side angle side test, in which if one angle is the same and the sides that are making that angle are in the same ratio. So the sides cannot be the same, right? If the sides are the same, then it is a congruent triangle, but we are just looking for similar triangles. So that means the sides will not be the same, but they will be in the same ratio. So for in this example that is given over here, the angle S over here and the angle L over here are same. So these two angles are congruent. So the so when we write equal to with a S above that, so this symbol is congruent, and when we write uh, just this, we write this symbol means similar. So as you can see over here, this the ratio for this side and this side, that is just 1 upon 1.5, is the same as the ratio of this side and this side, that is 2 by 3, because you can just multiply this by 2, and over here you will also get 2 by 3. So the ratio for both the sides that make this congruent angle are the same. So when this condition is true, then also you can say that both the triangles are similar. And finally, at last, we come to the SSS test. So SSS test is the side, side test. And in this, in this, we took the ratio of two of the sides and the angle was the same. In this, we just checked the ratio of all the three sides. So the ratio of PR and let us say XZ, and the ratio of PQ and XY and QR and YZ. So all of these ratios must be the same. So all these ratios must be the same. And then we can say that these two triangles are similar. So again, there are no proofs for these properties. There is a proof given for the AA property, but it does not, you do not have to remember this for the exam. You can remember this as this is a nice thing. And if you go through this once, you will also just solidify the understanding of the AAA test in your brain, but you do not have to go through this. So you just have to remember what the tests are. So if two angles are the same, or if angle and the sides that may are making that angle are in the same ratio, and finally, if there are all the three sides are in the same ratio, then you can say that the two triangles you're comparing are similar. And finally, there are some properties of similar triangles that are also given. So the first property is that any triangle is similar to itself, because of course it is. And then if one triangle is similar to the other triangle, then that other triangle is also similar to the first triangle. So this is called symmetry. The first property, that every triangle is similar to itself, is called the reflexivity. And finally, there is a transitivity. That means that if triangle ABC is similar to DEF and DEF is similar to GHI, then ABC is also similar to GHI. This is called transitivity. So now there are some more sort of examples. We are not going to go through those as we don't want to make the video too lengthy. And there's just one more theorem left in this chapter. So let's quickly cover that as well. So finally, the last theorem of this chapter is if there are two triangles which are similar. So we are already given that this triangle and this other triangle, they are similar. We are already given that. If that is the case, then the area of these two triangles are in the ratio of the squares of any of the two corresponding sides. So this is the statement of this proof. So the ratio of the area of the two triangles can be written as either the ratio of this squared upon this squared, or so that will be AB upon PQ whole squared, or this squared upon this squared. So AC squared upon PR squared, or finally this squared upon this squared. So BC squared upon QR squared. So now how do you prove this? So for proving this, you have to draw a little bit of a construction. But not too much. It's a very simple construction is that you just draw a perpendicular line from P to the base. So that is, you just have to draw a height of both of these triangles. And then what we do is, since we are given this angle is equal to this angle because they are similar triangles, obviously we are given that already, and the angle ABD is equal to the angle PQS. So this angle over here, ADB. So this angle over here, and PQ, PSQ. So these two angles over here are 90 degrees, and those are 90 degrees because we drew them perpendicular, right? We wanted to draw the height. So they just are 90 degrees because that is how we drew them. So since we know that these two angles are the same and these two angles are the same, using the triple double A test, the angle test, we can say that this inner triangle, this triangle over here, is also similar to this triangle over here. So again, I'll just repeat that what we are doing. We are trying to prove that the ratio of the areas of these two triangles can be written as the ratio of the squares of the corresponding sides. And what we are given is that these two triangles are similar. So the first thing that we do is use the angle test by using one of the internal angles and this 90-degree angle, and prove that these inner two triangles are also similar. And why do we do that? You'll just see that in a second. After we have proven that, we can say that the ratio of AD upon PS, that is this AD upon PS, this two ratio is the same to any other ratio of over here, over here, or over here, over here. Right? Because they are similar triangles. So that is by definition the case. That is what defines similar triangles. So because these two are similar triangles, we can say that PS upon AD is AD. This is D. I'll just write this again. AD is equal to either AB upon PQ, AB upon PQ, or is also equal to QS upon BD, QS upon BD, because these are similar triangles. So what we do is we write this equal to AB upon PQ. So that is just AB upon PQ over here. But these outer triangles are also similar, right? Because that was already given in the question. So AB upon PQ is also similar to is also similar to the ratio of the AB upon PQ is also the same as the ratio of this BC upon QR. Let me just reduce the clutter a little bit. So when I reduce this clutter, you can see that what we did was we just proved that this and this, the ratio of this and this is equal to the ratio of this and this. And because these outer bigger triangles are also similar, that means that the ratio of this and this is equal to ratio of this and this, or the ratio of this and this. And once we get that result, what we can do is just we can write the height of these triangles, the area of these triangles, as just the base into height, the base into height. So that is what we do. We write this as BC upon QR, that is the base, and AD upon PS, AD upon PS, BC upon QR, height into base. And then what we do is we just replace this. So this is the height. We replace this with the ratio of any other side. So this side, or this side. So we can replace this with BC upon QR. So then we get 2 times BC upon QR. So that means we get this squared, and we can follow the same logic to get the squares of any other sides as well. So again, you can see that the proof itself is not at all very long, but you just have to remember the steps of what you're actually trying to do. So you know that the area of a triangle is just base into height, and you can write that as AD into BC. And you're trying to prove the ratio of the areas, right? So you will write the area of the other triangle below. So that will be PS into QR. And to get these squares, what you have to do is you have to remove this height thing over here, that is AD and PS, and replace it similarly with the same thing you're trying to multiply it with. And why you can do that? Because these inner triangles are also similar triangles. So that is the basic intuition about this theorem. Again, being able to quickly write this in exam will only come with practice, but knowing the intuition behind this and the way of thinking to remember this theorem will really help you remember this in the exam. So after this, there are again only some solved examples, which we are not going to go through right now. Then there is this problem set. So that means we are at the end of the chapter. And finally, we reach the next chapter, Pythagoras theorem. So if you like this video and are preparing for your 10th board exams, the Maharashtra State Board SSC exams, don't forget to subscribe so you do not miss out on any updates. And in the next video, we are going to revise the chapter 2, Pythagoras theorem. Thanks for watching.